Hey, welcome to another problem session. Now, these are all coming to us from Indian JEE. This is 2020, and this is question number 2. This is what I call a smart question. This is a really good question, so let's look at it. All right. Um, there is a metal disc, uh, and you have a magnet, a strong magnet. Now, this disc can rotate by itself, and you can think of this magnet can be rotated, moved about. Maybe you can move the magnet about a different thing, and this disk will rotate independently. That's what it is. So as you're rotating, say you're rotating around like that, the question is this disk going to rotate in the same direction or in the opposite direction, or nothing will happen to it? Like, see, no, just temperature will remain unchanged. Maybe not rotate at all, but temperature will slowly rise. Okay. Now, all of these questions, if you have studied magnets and metals, you probably know what is called, there will be so-called Eddy's effect, or Eddy's current will be set up, right? When you have a magnetic field changing, if you're just a magnet next to a metal, there will be no Eddy's current. But if you move around magnet, which means you're changing magnetic field inside the some metal, then basically you send changing magnetic flux through any loop inside the metal, and the metal has a lot of conducting conducting electrons, and they will try to become a current, so they can have an induced magnetic field which will oppose the magnetic flux through those loops, any loop you pick up inside the metal, right? So that's the Eddy's thing. So how do we analyze this situation to answer this question? If it rotates, then we can rule out these two already. If it doesn't rotate, then we have to look at these two. If it rotates, then you have to see same direction, opposite direction. So let's see if it's gonna, definitely it's gonna rotate, because there will be current and there will be a magnet, and there will be force, and then there will be a torque. Let's see if that's really the case. So looking from the top, from above, so you have to give me some direction. Let's see, this is a disk, and over here I'm going to go just around here, so that area. So at some time t, it's over here. So sometimes let's see, sometimes t, it's over here. Of course, this thing is three-dimensional, so it's happening through we're looking at this whole area. Okay, so let's look at this disk. So you have a magnetic field going down like this, going down like this, going down like. So we can do magnetic field is like that, right, in that area, and magnetic field is 0 everywhere else. So this is at situation t, and a little bit later this magnet will be over in the next place. It's going to be over here a little bit later. So if you look at now the magnetic field is pointed in this whole area. So let's look at a couple. So this situation is t plus dt. Okay, so you have a couple of regions. You have a region here, A, B, C, D, then E, F, G, H. So if we look at A, B, C, D region, magnetic field has gone down, right? So, if this we look at this area, magnetic flux of the downward magnetic field, downward magnetic field has gone down. That means a current will be created in this loop, which will compensate for that. So which way the magnetic field has to be? So the current has to be, so eddy current will be, I want to use the right hand rule. So it's going to go this way. So they can create magnetic field down here, this way, and this way. So this is the current, this is I in this loop, okay? We can just call it just I, because we're just looking at effect, we're not trying to quantify it, okay? So we'll call I in every one of them. In this region D, C, D, F, E, F, so then there's a loop like this, C, D, E, F, B didn't change, phi B didn't change. Then you have this other loop where you have a E, F, G, and H. So in that loop, there used to be no magnetic field. Now there's a magnetic field. So phi of the B down went up. So that means we need to, Lenz's law will say you have to have current which will oppose that. So what kind of current will oppose that? A current that will oppose that will be create B up. The current I should create B up. So it should be in that direction here, that direction here, that direction here. That will be the loop that will create the current up. Induced magnetic field will be up, and here the induced magnetic field will be down, because compensate, it went down, so I need to make more of this. It went up, so I need to make the opposite of it. Now dt, if dt goes to 0, this will be as small as you like, So these loops will be next to each other. So let's write those loops next to each other. So you have A, B, C, D, and then you have E, F, G, H, E, F, G, H, and the currents that are being induced, current this way here, current that way, current that way, current that way, and then in this one they have a current this way, you have a current this way over here, you have a current, so this is, and current this way, and current this way. So you can see the force on these guys, these parts will cancel, force on these part of the loops will cancel. So now magnetic field is pointed down. So let's look, magnetic field is pointed down on this. That means when I do this current this way, I deal cross B to get the force. So I will have I with the B down. I with a B down. Oh, let me. So I with a B down. So over there, it's going to be a force will be pointed in on this part. On this current, force will be pointed that way, right? Because if this current pointed this way, magnetic field is down. So these forces will cancel, but these guys will gonna add. So if that's like current is that way, then magnetic force, when the current was this way, force magnetic force did I make this go this way, that way, and then so I had it this way down here. Okay, so and if this is the current direction and this is B direction, so it's going to be right hand rule. You know, you got to make sure right hand rule is correct. So right hand rule will say this going in that direction. So if this is going that way, force is in the same direction it's that going. So, and this is the radius of the lever arm. So this thing will also rotate that way. So it's going to rotate in the same direction. So B is the answer. So actually it looks like everything else is not contributing. It's just that middle part of this whole bunch of loops. These just representative loops, but there will be a whole bunch of loops like this, eddy currents like this. They all force on the middle part of the eddy current loops will all be pointed in that direction of the disk, looking from the top, if this thing is rotated in that direction. So B is correct. This is a pretty good and cute problem because rotating, we don't need to worry about C and D. Okay, they are wrong. All right, it's a good problem. I will see you another video. Okay, bye.